Let's take some of the objective problems. So we are now discussing the objective problems. So let's take an example. Here the weight W is suspended with the help of two cables. The weight W is suspended with the help of two cables. Here the one cable is making an angle theta, another cable is making an angle 60 degree. And suppose tension in these cables are T1 and T2. And now we are interested in the tension in the cable making an angle theta will be minimum when the value of theta is right, means we are interested in when T1 will be minimum, when T1 will be minimum for which value of theta, when T1 will be minimum for which value of theta. So now we can apply the Lami's theorem for this case. So this angle is 90 plus theta. This angle is 150 degree, and this angle is nothing but 180 minus 60 minus theta. So by applying the Lami's theorem, T1 by sine 150 degree equals to T2 by sine 90 plus theta, W by sine 180 minus 60 minus theta. So one by one we will take. If we take two equations, T1, T2 into sine 150 degree, and this one is sine 90 plus theta. So for T1 minimum, this sine 90 plus theta will be maximum. In that case only the theta T1 will be minimum. For T1 minimum, sine 90 plus theta will be maximum. So theta should be minimum in this case. Then only sine will be approaching to the 90 if theta will be minimum. Suppose 90 plus something is equals to the nearly equal to the sine 90, then sine 90 will be having the maximum value. That's why I am telling for T1 minimum, sine 90 plus theta will be maximum, and maximum value will be 1. So 1 only in case of sine 90, so theta should be minimum in this case. Similarly, if we take T1 equals to W sine 150 degree divided by sine 180 minus 60 minus theta, or we can rewrite this thing W sine 150 sine 180 minus 90 minus 30 plus 60. So we can write this thing W sine 150 degree sine 180 minus theta is nothing but sine theta, 90 minus 30 plus 30. Again for T1 minimum, sine 90 minus 30 plus theta will be maximum, and sine 90 minus 30 plus theta will be maximum for theta equals to 30, because at theta equals to 30 we will get sine 90 minus 30 plus 30 equals to 1. Then only t1 will be. So correct answer is theta will be 30 degree. Let's take another objective problem. See, the problems are objective problems, but I am describing more for your understanding. So don't think about it is a subjective problem, it's an objective problem. So let's take another problem. There is a heavy rod AB of length L, and weight is W. The weight of AB is W, is hinged at the point A. It is hinged at the point A and is tied to a weight W1 by a string W1 by a string here. At B, the massless string pass over a frictionless pulley. At C, that is C, if the rod is in equilibrium, then we have to find out relation between W and W1. I will again repeat this question. There is a rod AB. The length of the rod is L. Weight of the rod is W. One end of the rod is hinged at point A and second end, that is B, is attached with the help of a string, and this string is passes over a frictionless pulley, and here a weight W is hanging on it. And again this length is given, that is L. So by this diagram, this is L, this is L. So with the help of trigonometry LL, so we can find out this angle will be 45 degree by theta equals to tan inverse L by L. So this will be tan inverse of 1, so it will be 45 degree. So this angle is 45 degree. Now we have to find out relation between W and W1, and we have to assume that AB will be in horizontal position. Means we are not going to change the position of AB. It means it is in equilibrium, so we can apply the condition of equilibrium. So I am applying the condition number 3. Algebraic summation of moments of all the poles about A should be 0. So at A there is a hinge. So hinge reaction, the moment due to hinge reaction at A will be 0 because line of action is passing through the same point. So now we have to consider the other forces. But before applying the condition of equilibrium, let's draw the free body diagram. AB. So free body diagram of AB. Here we can say that here there will be reaction RAX. There will be reaction RAY. The weight will act at the center of gravity, that is W, L by 2, at L by 2. And here the force is acting here. It is nothing but W1. Tension in the string, we can say that. And this angle is 45 degree. Now we can apply the conditions of equilibrium. So remember one thing, before going for directly applying the condition, first draw the free body diagram. Now it's very clear. Now we are interested in algebraic summation of moments of all the force above A. So if we see at A point there are RAX and RAY, and line of action of RA and RAY is passing through A. So perpendicular distance is 0, so moment will be 0. So I can write RAX into 0 plus RAY into 0. And if we talk about moment due to W at A, so we have to multiply this W with this perpendicular distance, that is L by 2. So W into L by 2, and this moment will be in clockwise direction. So according to our sign convention, it is positive, and anti-clockwise will be negative. So this one is positive. And for W1, we are having two components. One is W1 sine 45, and second one in that direction, that is W1 cos 45. So due to W1 cos 45, the moment will be 0 because perpendicular distance is 0, and moment due to this W1 sine 45, perpendicular distance is L, because this into this distance L by 2 plus L by 2, this one L, and it is in anti-clockwise direction, so negative is to 0. So now if you see, it will W into L by 2 plus 0 minus W1 sine 45 is 1 by root 2 into L equals to 0. So we will get W by 2 equals to W1 by root 2. So W1 will be W1 W root 2 by 2. So W root 2 root 2 by root 2 will get W by root 2. So this one is the relation between W1 and W. This W1 equals to W by root 2. So this one will be the correct answer. Problem of engineering mechanics, which is asked in GATE AMI 2009. Now we will solve this problem. A block of weight 981 Newton is resting on a rough horizontal surface. It's resting on a rough horizontal surface. The coefficient of friction between the block and the horizontal surface is 0.2. A vertical cable is attached to the block, provides partial support as shown in figure. That is the vertical cable going for partial support, and the T is the tension in the cable. A man can pull horizontally with a force of 100 Newton. So we have to find out the value of T if the man is just able to move the block to the right. We have to find T if the man is just able to move the block to the right. Block to the right. So again I will repeat this question. There is a block, weight of the block is given, that is 981 Newton. It is resting on a rough horizontal surface. The coefficient of friction between this block and the surface is 0.2, and vertical cable is attached to this block to giving a partial support, and the man can pull horizontally with a force of 100 Newton. So we have to find out what will be the value of T if the man is just able to move the block to the right. Just able to move means the body is in limiting equilibrium. So we can treat this problem as a problem of equilibrium, and before solving the problem of equilibrium, the first step is we have to draw the free body diagram. Free body diagram of block. So in free body diagram of this block, we are having the weight 981 Newton, which is acting in the vertically downward direction. The block is in contact with the surface, so there will be reaction R. Already there is a tension T, which is having the same direction as the reaction. Here we are having 100 Newton, and the block is just able to move in the right direction. So the frictional force will be here. There will be a value mu, which are this normal reaction. So now we are interested in the value of T. So we can apply the conditions of equilibrium here. So for conditions of equilibrium, first apply sigma fx equals to 0. It means algebraic summation of all the forces about x-axis will be 0. So algebraic summation of all forces about x will be 0. I am defining our coordinate axis xy, that is positive x, that is negative x, that is positive y, and this one is negative y. So now we can easily apply the condition number first. So in horizontal direction, or we can say that in x direction, there is a force called mu r. It is acting in negative x, so minus mu r. Another force which is acting in x direction is 100 Newton. Positive direction, so plus equals to 0. So R will be 100 by mu. So 100, the value of mu is 0.2, and if we calculate 100 divided by 0.2, so it will come around 500 Newton. So by this way we can get the value of R, that is 500 Newton. Now we can apply the condition number 2. Algebraic summation of all vertical forces should be 0, or we can say that algebraic summation of all forces along y direction will be 0. So in y direction we are having R, which is acting in positive y, so positive. We are having T, which is again acting in positive y, positive. Then we are having 981, that is in negative y, so minus equals to 0. So T will be 981 minus R. So T will be 981 minus 500. So it will be 481 Newton. So by this way we can easily calculate the value of T. So T equals to 481 Newton will be the correct answer for this problem. So by simply drawing the free body diagram and applying conditions of equilibrium, and with taking the proper sign, we can easily get the value in a minimum interval of time.